Welcome everybody. Welcome to our another lecture in algorithmic analysis course. So today we will discuss red black trees. Okay, so we'll discuss about red black trees. This is a kind of data structure actually in this course, but this course is algorithmic analysis. Okay, so we will discuss in context of the efficiency of the algorithm of red block trees not in depth about the implementation of in red block trees. Okay. So again I'm using Dr. Lee's lecture slide. I would like to thank her again. So if we go to the book and search for red block trees, and you see that it is in chapter 13 of our book, and then if we jump over here, can we jump over here? Okay. I got it. So red block trees. So in our previous lectures we discussed binary search tree, right? So we discussed binary search tree, that a binary search tree that can have maximum of 2 child. By means 2, right? So it can have maximum 2, it can be 1. Okay, it can be no child, but it can have maximum two child. Okay, that is a binary search tree. And then we discussed that there is a limitation of a binary search tree. Okay, for instance, if I have my data set, it comes at 1 2 3, then 4 5 and 6, this way for a binary search tree. So the first element will come as a node, so that first one will come over here, 1. Okay, node 1, and then second one is greater than, so it has no child, right? It has no child actually. Let me the first node with value 1 will come over here, it has no child. Okay, so the left child and right child are empty or null. Okay, and then 2, it greater than 1, so it will go to the right side, so 2 will come over here, and then 3 it will go is greater than again 2, again 1 and 2, so it will go to 3 this side, and similarly 4 will go this side, and 5 will go on right side, and 6 will go on this side. So this is a BST. Okay, BST. Okay, but we discussed that this is the limitation of BST, that in order to search an element, for instance 6, we need to go all the way starting from the first node, then we'll jump to the next node, next child, and we need to go all the way into the tree, so that in this tree this height equal to n, right? Height equal to n, and then actually, and then we can, or we can say big O of n, whatever you say. But this is an imbalanced binary search tree, that, and otherwise we discuss that. Otherwise, for instance 5 4 6 like 3, and then okay, for instance this 7 okay, this could be a this is empty. Okay, this could be a pretty balanced by binary search tree, and its height will be pretty much big O of log n, right? So height will be less. But this height is the larger, right? So this is inefficient. Still it needs binary pretty linear search. Okay, in order to resolve this issue in binary search algorithm, and then in our previous lecture we discussed AVI tree, right? An AVI tree is a binary search tree, but that has self balancing, and also what that we discussed the other properties and rotation, okay, for AVI trees. actually, for in order to understand red block trees and its implementation, you need to understand AVI tree first. If you understand better AVI tree, that will be better. So you can go ahead, please, to my previous video to watch that first. Okay. so So these are the properties of read block trees. I like you to read the book, and also you can go to the slide also. So what we want to do, we know this binary search property of the binary search tree, right? This one. every node actually in shortcut I say every key node, so what is the value, every node in the left subtree, you can instead of calling left side, left subtree is better. Left subtree is less than its root value, and every value on the right subtree is greater than is root value. Okay. And one thing there, another limitation in BST is that it cannot hold duplicate value. If a value is h, and then you cannot have another h. Okay. So we know that in the binary search tree, in an worst case, we for complete binary tree, okay, log n its worst case is, but for linear chain, that is for the worst case, it will be big O n, right? So this is that what we discussed here in a minute ago. Okay, so in order to resolve that issue, we discussed AVL tree, and now we'll discuss red black trees. So red black tree is another improved version of binary search tree that actually ensures balanced. That ensure is balanced, and that ensures that its height will be big O of log n. Okay, so this is a quiz question. This may be a quiz question. Okay, a test question. Okay. So what is a red block tree? So is red black tree, sorry, not block, red black tree is a binary search tree, okay, that augmented with node color. Okay, so it has node color. Some nodes are red color and some nodes are black color. We will discuss this soon. Okay, and it is a balanced tree, BST, and it balance. Since it is balanced, it ensures that it guarantees that the height will be big O log n. That means maximum. Big O means maximum, right? In the worst case, that maximum height will be log n. Okay. So so we need to understand what are the properties of red black trees, and then we need to prove these guarantees that height will be big O log n, and finally we discuss the operation of red block trees. Maybe we can go shortly. And from the book, actually these are the properties of red block trees. So what is that called? Every node is either red or black, but except the root node. Root node must be black. Okay, and every leaf, that nil node, is black. Okay, then if another condition is that if a node is red, then both its sides are black. That means if a node is red, then its side cannot be red. Okay, so both of its children are black, and for each node, all simple paths from the node to the descendants leaves contains the same number of black nodes. I will show you this. What does this mean? So I think in the book we find some demonstrative. Then it's good. Okay, so here you see that. So it says, okay, so this is a black and white book. So I think consider that these are black. Okay, so these are black and these are red or white. This white or red. Okay, so then root node is black, and if a root a node a node is black, then its subsequent children node can be black or red. But if a node is red, then it both children must be black. And all leaves node, this one leaf node, and this one leaf node, this one leaf node, this one leaf node, no matter whether they are whether they are black or red, the leaf node has the nail node that are black. Okay, so these are the 5 properties. Okay, so this will be a test question, so you need to memorize this part, this one, this side question. Okay. So every node is either black or red except the actually root node. Actually the root node is always black, and every leaf node, leaf pointer is black. And if a node is red, then both children are black. And if that means it does not say that if a node is black, then both children are need to be black. So it does not say that both children can be either is black or red. And this is the property 5 number. It says in either way, so descendants contains the same number of black nodes. So for instance, we see that in the left side, if you go on the left, how many black nodes over here? Actually this is a large I can go with an easy example. Okay. So this one, so let us see, it fits all the properties. Okay, so a, this is root, it is black. Okay, so then this is another node. So if you black, then it can be black or red, right? So and then this is nail, this is nail, so this is the leaf, this is leaf, this is leaf. So all of this leaf has nail, and this is black nails are black. And then if a node is red, then its children, both children must be black. So these both children are black, so right? Okay. And another thing is that the number 5, property number 5 is that what it says, this one. So for each node, all simple paths from the node to the descendants leaf contains the same number of black nodes. So starting from here on the left side, how many black nodes? 1, 2, right? So and from here in this path, how many black nodes? 1 and 2. And then for this path, how many black nodes? So let me draw it. So for this path, 2 black nodes. For this path, 2 black nodes. For this path, 2 black nodes. And for this path, 2 black nodes, right? For every path, okay, it has 2 black nodes. And for this one, starting from here, it has 1 black node, it has 1 black node. So it has 1 black node, it has 1 black node. That is the number 5 tells that. Okay. Okay, so the a node, so what is the black height? A node x down to the leaf, the black height of the node is called black height. Actually we need black height, and then a node from down to the leaf, the black height of the node. Okay, so actually let us see this. Okay, so actually main thing is that then in the red black tree, that you understand, right? Every node is either red or black. That means in addition to to the node value, okay, every node contains is color also, right? One more identity, right? Color also. Okay, this color can be implemented with boolean values. For instance, you can say 0 for red, and then 1 for black, or 1 for black, 1 for red 0 for black, no problem, or you can increment with any type integer type variable for the color. Okay, so here let us check that this checks just properties. So all root leaves, the root leaf is black and all leaves are black, right? All leaves, so nil leaves, okay, these are black. Okay, if a node is red, so we are checking whether it is a black, red black tree or not. If it is red, then its both child need to be black, so right, so this both side needs to be black, it's okay. And then so black height, so for all simple path from any node x to a descendant leaf have the same number of black nodes. First, this is called black height. Okay, so here black height, this side is 2 and this side is 2 and this side is 2, but this side is 2 for any path. It says for any path. Okay, that means we can say for all paths, actually for any path same, it should be same. Okay, so then what is the question? This question is that what is the minimum black height of a node with height h? Okay, think about a second, what is the answer of this one? Okay, it will be greater or equal to 2. Actually that we can say in, you can take in is by 2, we can okay, I'm sorry, we can take ceiling. Okay, the height each node has black height has is greater or equal to n by 2. Okay, then there is some existing theorems that people they prove this. A red black tree with n internal nodes has a height that is less or equal to 2 log this is base 2 lg n plus 1. Okay, we don't need to prove it for now. So let us see that let us prove is intuitively this one. Okay, so let us see this red black tree. So this is a red black tree, right? So this is black, this is black, so this is red, these both are black, and then these are red, and it's okay. So one, no, this is a red black tree. Okay, actually still in the margin. Okay, actually it is still in the margin. Okay, margin means you just move off this from this right subtree to the up to the top, then it will what will be happen over here. So these two will go over here, this one will go over here, and then this one will go over here, and then even again if you merge it, then it will be like this. Okay, so then the merging will be like this. So actually I think we should read the book for this theory. Let us see in the book, it has more description. So this is the thing, this is the this is the algorithm. Actually we are not going to its proof. Actually the slides are some intuitive proof. Okay, okay, so then what will be the advantage of red block tree, as that it will ensure guarantees that the height will be maximum of height will be log n. Okay, so then bigger log n. Okay, and then in order to uh, implement that guarantee that the height of a red block tree will be bigger log n. Actually when we develop a red block tree, then we need to do frequently rotation. How do we frequently do rotation? That means whenever we need to build a red block tree, we need to maintain these 5 properties, and if we follow these 5 properties, then the tree will be red block tree, and it will be guaranteed with height uh, of log n. Okay, so the book, so I like you to go detail, read these few pages for the properties, and then this intuitive example, and this is the theorem. Okay, okay, now we want to discuss the rotation of red block tree briefly. Actually this course is not a data structure course, so we are not going to in-depth discussion or of the implementation. Okay, so you see the rotation. Actually I'm coming back soon here, but here, so why do we need the rotation? We have rotation algorithm. Okay, we have rotation algorithm, and then actually in my previous lecture with AVL tree, I discussed there are 4 kind of rotations, right? We will need this here, we will need that here in this lecture. So actually let us go to a new lecture, and then in the next lecture we will discuss the rotation of red block tree. Is okay, and thank you so much.